Hi class. So today we're going to continue talking more about game theory. In particular, we're going to introduce what's called a mixed strategy, and we're going to learn about expected value in order to try to see which mixed strategies are the best. This is going to help us analyze games where there's not a saddle point. Remember last time we saw if there was a saddle point, then the games were not so interesting because both players were incentivized to just play it safe, and we'd always get that saddle point as the outcome. Most interesting games, like rocks, paper, scissors, like odds and evens, and most games that will come up in real life, do not have saddle points. And this leads to tension between the players trying to outguess one another. But it turns out that we can still analyze these games, and it turns out we can solve for an optimal strategy even when there's this aspect of luck and randomness, which is pretty amazing. So let's take a look at the game. It's very easy. It's a carnival game, okay? And you get to flip a coin, and if you flip a heads, you win, let's say, $10. Great. And if you flip a tails, you lose $20. It's a carnival game, right? You know, those are always rigged against you. Okay. So what I want to do is I want to see, if we play this game 10 times, how much money should we expect to win or lose? Okay, and there's a lot of different ways to think about this. Without involving any probabilities, there's actually a clean way to find this out. Half the flips should be heads. We can expect that. Okay, so that's 5 flips to be heads. So 5 flips should give us plus $10. And we can expect half the flips to be tails. So again, 5 flips should give us minus $20. Okay, so in total, how much money are we going to make? We're going to make 5 times 10, and then we're going to lose 5 times negative 20. So we just have 50 minus 100, get negative 50. So we can expect to lose $50 overall. Now if I divide this by the number of games that we played, then we see that each round we can expect to lose $5. Now this is a little bit weird because remember the outcomes were heads plus $10 and tails minus $20. So none of the outcomes could actually give us a negative 5. But this is just saying in the long run, after we play this game multiple times, every single time we play it, we lose on average $5. And so this is the expected value of the game. And this is how carnivals and casinos make money. The expected value of every time you pay is going to be negative. So even if you do flip a heads, and you get $10, well, in the long run, that'll be counteracted by tails. And so in the long run, this game will make money for the carnival, or will make money for the casino. So all games in the casino have a negative expected value. It's not to say that you can't win those games, it's just to say that in the long run, you will lose money. Okay, so we're very upset. We lost about $50 to this carnival game. Next time the carnival comes to town, we decide we're going to try to cheat the system. All right, we bring an unfair coin to the carnival. Okay, so, I know somebody, he makes coins that will flip heads way more often, okay? So when we flip this coin, we get heads 4/5 of the time, and the remaining 1/5 will get tails. Okay, so now is this coin, right? Remember, heads gives us $10. Is this coin going to be biased enough that maybe we can make money off of this game. Okay, so let's analyze this. A heads will give us plus $10. A tails will give us minus $20. But now, the probability, so here's the outcome, the probability that each will happen is no longer half and half, right? That's what it was before. Now it's 4/5 that heads will happen, 1/5 that tails will happen. And so say we play 10 games, how many of the times can we expect to flip heads? Well, 4/5 times 10, which is equal to 8 heads flips, we can expect. And 1/5 times 10, which is 2, should be tails. So how much money will we make? Well, we'll make 8 times 10 plus 2 times negative 20. So here we get 80 minus 40. This actually turns out to be plus 40. So over 10 games, we can expect to make $40. Right? And that's great, right? Now we're winning money. Okay? I mean, they might get a little suspicious. And this isn't to say we'll always make money, right? It's sort of the gambler's fallacy that the expected amount of heads and tails will be the actual amount of heads and tails. This isn't going to always be the case. We might flip fewer heads than expected or more heads than expected. That's why we use this word expect. This is what we expect to happen, just like before we expected half and half, but that doesn't need to be the case. If I flip a coin 10 times, it probably won't be 5 heads and 5 tails, right? I might get 6 heads, 4 tails. I might even get really lucky and get 10 heads and 0 tails. Okay, so back to the problem. Over 10 games, we expected to make $40, so each game we play, we expect to make how many dollars? Well, $40 over 10 games, that's just $4. Now that's great. That's saying we should play this game as much as possible because every time we play it, we're going to be up $4. Again, I'm not saying that we win $4. It's impossible to win $4. You either win $10 or lose $20. I'm just saying in the long run, every game we play, we can expect to be up $4. And so what we've been looking at is this thing called expected value. And what is the expected value? Expected value is outcomes weighted by their probability of occurring. So think about with the example with the fair coin, we have heads and tails, and the outcomes for flipping a heads was plus 10, tails was minus 20, and the probability was half and half. And so if we just go across and we multiply the outcome by the probability, we'll get 10 times 1/2. And then here we'll get negative 20 times 1/2. So this is 5, and this is negative 10. If we add all of these up, then we get a negative 5. So this is the expected value of these outcomes given those probabilities. And if you scroll back up, you'll see this is exactly what we calculated. We expected to lose $5 each round. Right, so this is just a shortcut for doing that analysis that we did above. In that second example, with the unfair coin, right, the outcomes were the same of plus 10 and minus 20, but we switched up the probabilities by using an unfair coin. That was heads 4/5 the time, tails 1/5 the time. And so what was the expected value? Here, 10 times 4/5 plus negative 20 times 1/5. So here I get 8, and here I get minus 4. So altogether I have a plus 4. Right? So expected value to win $4 each round. And so these numbers here are my expected value of these two different games. Let's do one more example. This will be with a new game. Okay. Say we're just going to roll a dice. If we roll a 6, then we win $12. Otherwise, we lose $1. Okay, so here's a question. Someone comes up off the street and asks you this. Hey, you want to play a game with me? You get to roll a 6-sided die. If you roll a 6, then I'll give you $12. Otherwise, you got to pay me $1. Now, how do we decide whether or not we want to take this person up on their game? Well, let's just calculate the expected value. So what are the two situations? Well, we can roll a 6. And the outcome of rolling a 6 would be to get $12. Or we could not roll a 6, roll 1 through 5, then the outcome would be negative $1. We'd lose $1. Okay, well, what's the probability of these events occurring? Well, let's see. What's the probability of rolling a 6? Well, I need to choose one number out of 6 options. So I have a 1 in 6 chance to roll a 6. So what about rolling a 1 through 5? Well, I have 5 options out of a total of 6, and so the probability here would be 5/6. Okay, now let's calculate the expected value of this game. Okay, it's going to be that 12 times that 1/6 plus negative 1 times 5/6. And so sometimes we'll abbreviate this EV. The EV is just going to be 12 over 6, which is 2, minus 5/6, which in this case will end up being 7/6. Which, if we convert it to a decimal, is $1.17. So each time we play, we can expect to win $1.17. And so should we play this game or not? The answer is yes. In fact, I want to play this game 1,000,000 times, and then I'll probably be a millionaire. All right, the person who is proposing this game to you, probably some crazy person, because they don't understand that they're going to be losing a lot of money by playing this game with you. So let's see how this idea of calculating expected values can help us better understand how to play games with one another. And so I want to introduce the idea of a mixed strategy. And this is opposed to what's called a pure strategy. So let's use the example of odds and evens. Okay, a pure strategy just means we're going to continue to select the same choice over and over again. So if I want to use a pure strategy of 2 fingers, that would just mean I would throw out 2 fingers every single time. Okay, notice that that's a pretty bad strategy. If I did that, someone would catch on to me and they'd probably start, throwing whatever they needed to win. Okay, so pure strategies are usually not very good. It's just saying I'm going to select one choice and I'm just going to do it over and over and over again. And what's a mixed strategy? Well, it just means that you're going to mix things up. So you're going to switch between your choices. So sometimes we'll throw 1 finger, and sometimes we'll throw 2 fingers. And so this is what most everyone was doing when they were playing this game. It was obviously just intuitive that we need to change our strategy up. We need to mix our choices in order to try to win. So this next game I want to introduce is one that, well, we haven't seen much of, mostly because all sports have been canceled. Okay, but I want to think about a baseball duel. Okay, the batter going up against the pitcher. Now we'll play as the batter, so the batter will be player 1, pitcher will be player 2. And so the pitcher can choose to throw a fastball or a curveball. So those are the two options that the pitcher has, and the batter can decide whether to guess that the pitcher will throw a fastball or guess that the pitcher will throw a curveball. Now, if you know a little bit about baseball, you'll know that the pitches are so fast that there's not a lot of time for a batter to read what the pitch is while it's coming. So they do really need to make a guess about what the pitcher will throw before they even analyze the pitch at all. And of course, if they guess correctly, then they'll have a higher chance to hit the ball, but they can still hit the ball even if they guess it wrong. So in this scenario, let's say if the batter decides to guess that the pitcher's doing a fastball, and he's correct, so the pitcher also throws a fastball, then the batter has a batting average of 300. If you don't know what a batting average is, it's just the probability that the batter gets to hit the ball. So 3 out of 10 times the batter will hit the ball if he guesses correctly on a fastball. On the other hand, if the batter guesses correctly on a curveball, and the pitcher throws a curveball, that is, then the batting average is significantly higher. Right? Curveballs move a lot slower than fastballs. And so if the batter guesses correctly, a curveball's coming, pitcher throws a curveball, batter has a really high chance, like a 50% chance to hit the curveball. So what happens if the batter guesses wrong? Well, if the batter guesses a fastball, but the pitcher throws a curveball, then they can still hit the ball, but with only a batting average of .200. So they have a smaller chance to bat it. And if they guess curveball, but a fastball comes, that ball's coming so much faster than they thought it was going to come that they really only have a 100 batting average against that. And so the question with this game is, what should the batter guess and what should the pitcher throw? Right? We can play from either side. And the point is that the batter wants the highest batting average they can get. And the pitcher wants the lowest batting average. Okay, so before we even talk about the mixed strategies, let's do the analysis that we've actually already learned to do. Right? Let's find the minimax and the maximin strategy. So the maximins, I go across each row and I find out the minimum value. So in the first row, the smallest number is 200. So if the batter guesses fastball, then the worst they can do is have a batting average of 200. And if they always guess curveball, the worst they could do is have a batting average of always 100. And so out of those two numbers, 200 is the larger one. So this is the maximin value. What's that saying? That's saying that the batter's safest strategy is to always guess fastball and get a batting average of 200, 0.200. On the flip side, let's find the minimax. So find the column maxes. And this is from the point of view of the pitcher now. Well, if the pitcher throws a fastball, then the worst thing that can happen is that the batter always guesses fastball, in which case the batter will have a batting average of 300. And if the pitcher always throws a curveball, then the worst thing that could happen is the batter always guesses curveball, in which case the batting average will be 500, which is much better than 300. So the pitcher's safest strategy is to always throw a fastball. So the pitcher's safest strategy. And here, I'll just call it what it is. It's the Minimax strategy. It's to always throw fastball and get a batting average of at most 300. Okay, maybe the batter guesses curveball the first couple times, so it doesn't hit all the fastballs, but the batting average will be at most 300. Okay, but if you're on the team and your batting average is 200, right, this is not going to cut it. Okay, you're not going to be starting much longer. And similarly, if you're a pitcher and you're pitching a batting average of 300, it's also not really going to cut it. Okay, that's a little bit too high of a batting average to have against you as a pitcher. So both the batter and the pitcher want to do better than this. So how can they do that? Well, they can mix up what they're going to throw and what they're going to guess to try to get a higher or lower batting average. Okay. Notice that in this game, there's no saddle point. Right? The maximin was not equal to the minimax. The maximin being 0.200 and the minimax being 0.300. And again, that's just to say that this is actually an interesting game to play. So let's use a mixed strategy. Okay, so let's say we're the batter. Instead of always guessing fastball or always guessing curveball, I'll guess fastball half the time. And I'll guess curveball half the time. So how are they going to decide half and half? Well, they could like mentally flip a coin, however they want to. And so what's the expected value of this mixed strategy? And here we need to be a little bit careful because we don't actually know what the pitcher's going to throw, right? So the batter is half the time going to be in this first row and half the time going to be in that second row, but we don't know which column we're going to be in, right? Sometimes the pitcher will throw a fastball, sometimes the pitcher will throw a curveball, and we don't know. We just know we're going to either give ourselves the option of 0.3 versus 0.2 or 0.1 versus 0.5. We're going to do that in a half and half split. So what we'll do is we'll calculate the expected value if the pitcher throws a fastball, and we'll calculate the expected value if the pitcher throws a curveball, and we'll use both of those numbers to try to analyze the game a little bit more. So we're going to be in this 50-50 split, but we're going to restrict ourselves to the case when the pitcher throws a fastball. So versus the pitcher throwing fastball. Okay, so here again, batter, guessing fastball versus curveball. Pitcher, we're going to restrict ourselves to only being in that fastball column. So the batting averages were 0.300 and 0.100. And now I've said that I'm going to each of them with probability 1/2. So here's the probability of 1/2, 1/2. Now look, these are the outcomes, and these are the probabilities that they'll happen. So the expected value just comes from multiplying across. 0.300 times 1/2, 0.100 times 1/2. This is 1.150. Now this one is just 0.05. Now we add those together to get the expected value, and the expected value of 200. So if the pitcher throws a fastball, and half the time we guess it's going to be a fastball, and half the time we guess it's going to be a curveball, then we can expect to have a batting average of 200. That's what this is saying here. Well, what happens if we're in that other case? What happens if the pitcher throws a curveball? Well, okay, again, the batter is choosing between fastball and curveball, but now the pitcher is only going to throw a curveball. So let's take those values back up from this column up here. Instead of being in that fastball column, I'm going to be in this curveball column. Okay, so the numbers are 0.2 and 0.5. And again, these are the outcomes, depending on whether I choose fastball or curveball. And the probabilities are going to be half and half because that's my mixed strategy. My mixed strategy is to do it 50% of the time for both. So what's the expected value? Well, this is 0.200 times 1/2, 0.500 times 1/2. So I get 0.100 here, I get 0.250. And if I add those two up, I'm going to have a expected value of 0.350. So what's that saying? If half the time I guess fastball, half the time I guess curveball, and the pitcher throws a curveball, then I'm going to have a really high batting average, one of 0.350. And so if you look, what have we concluded? If the pitcher throws a fastball, I'm going to get that batting average of 200. Okay, that's not great. But if they ever throw a curveball, I'm going to get a batting average of 350. And so compared to my Maximin strategy, remember, what was our Maximin strategy? It was just to guess fastball all the time. But if I guessed fastball all the time, then I would probably only get a batting average of 200, right? I'm doing no worse against a fastball. I'm going to do way better against curveballs. And so this mixed strategy, which I'll describe as half fastball and half curveball guessing, gives us no worse of a batting average and a better batting average against curveballs. And so we'll see that we can use this idea of mixed strategies and expected value to actually figure out what the best mixed strategy is. Okay, this is one mixed strategy, and we can see how it does against both of the pitcher's pure strategies. Right? When I say the pitcher is always throwing a fastball, this is a pure strategy from the pitcher of only throwing half. Pitcher throwing a curveball is a pure strategy. So we're measuring how this mixed strategy does against some other pure strategy. And we can use this, and you'll see next class that we can use this to find the best strategy, the best mixed strategy from the batter. We can tell the exact percentages that the batter should guess fastball and curveball to get the absolute highest batting average overall.